Good morning, dear students. Uh, in the last period, we have studied about the thermodynamic function, which is called enthalpy. Let us revise the topic and then we'll move forward. So, enthalpy is a useful state function. We are already aware, my dear students, that if the heat is exchanged at constant volume, we consider it as a change in internal energy. But most of the chemical reaction we do in the laboratory or we do at constant pressure. So, for example, if we have a gas container, in this gas container, we have filled some gas at constant pressure. This gas has got a piston which is weightless and frictionless piston, and thus in the gas container we have the gas at atmospheric pressure, the outside pressure is atmospheric pressure, and the volume of the gas is V1. Now, my dear students, we start heating it. As we heat it, there are two changes that majorly takes place. One of them is increase in volume from V1 to V2 and increase in temperature from T1 to T2. Due to this, the internal energy, due to change in temperature, the internal energy even changes. So now you can see in the next figure that the volume from V1, it has been now increased to V2. You can see this is volume V1 and this is the volume V2. So this is the change in volume delta V, that is V2 minus V1. So this is the volume of the gas or gas expanded. And still the outside pressure is P that has been made constant. That means the change what we have brought is at constant pressure. So before heating, my dear students, or in the initial state, the temperature was T1, pressure P1, volume V1 and internal energy U1. After heating, my dear students, you can even see that the temperature is T2, pressure P, volume V2 and internal energy is U2. So you can still see in both the cases that we have our pressure that has been maintained constant. So in both the cases, either in the initial state or in the final state, the pressure P remains constant, and that is why we do this change at constant pressure, or we can call it as an isobaric change. As the heat is absorbed by the system, we can say that heat absorbed is equal to QV. We already know that heat absorbed by the system at constant volume is change in internal energy. But here, the heat absorbed by the system is at constant pressure, my dear students. So as the heat is absorbed at constant pressure, we would call it heat absorbed at constant pressure QP. Let us see. Type of change is change at constant pressure, which is an isobaric change. So here the change in the heat absorbed is utilized to bring about the following changes. Volume is increased from V2 to V1 and temperature is increased from T2 to T1. Now some of the heat increases the kinetic energy of the molecule and thus bring more strong force of heating, and due to which the piston moves upward and the volume changes. Before piston moves upward, the kinetic energy of the gas particle increases to such an extent that the force per unit area, that is the pressure of the gas, is enough to move the piston. The increase in kinetic energy brings about the change into the temperature of the gaseous molecules. So at the temperature T2, piston moves upward and during the change both the temperature and volume keeps on increasing. So now let us understand the changes mathematically. We can see that change in internal energy is U2 minus U1, change in volume is V2 minus V1, pressure remains constant, the work done is minus P delta V. The negative sign shows that the work has done due to the expansion, or it has got the negative sign. Heat absorbed, that is your QP, and that is why, according to the first law of thermodynamics, that delta U is equal to Q plus W. Now here W is minus P delta V, and Q we represent it as a QP because heat is exchanged at constant pressure. And for delta U we can write U2 minus V1, and for delta V we can write V2 minus V1. And finally, by um, by solving the equation or by making it more simple, you can find out, or we can find out, that U2 minus U1 is equal to QP minus PV2 plus PV1. Again, on the more simplification, my dear students, we find that U2 plus PV2, that is U1 plus P1 plus QP, and finally QP is equal to U2 plus PV2 minus U1 plus PV1. Ultimately, we call it as a delta U plus PV. And this is what it makes us to introduce a new thermodynamic function. So now we can define another thermodynamic function, which is known as enthalpy. Uh, what is enthalpy? If we really understand, word enthalpy comes from the Greek word enthalpion, that means to warm or to heat. So this new function, enthalpy function, is your H, that is U plus PV. The new thermodynamic function enthalpy H is mathematically written as H is equal to U plus PV, which is for initial state of the system. That is, for initial state we can write H1, and for final state we can write the enthalpy H2, and that is why change in enthalpy we will call it delta H, that is your H2 minus H1. And we know that H is equal to U plus PV, and thus by writing the change delta H is equal to delta U plus delta PV. Delta PV, it means delta P into V or P into delta V. But delta P is zero because we have kept the pressure zero, and that is why delta P into V is also equal to zero. And finally, we have delta H is equal to delta U plus P delta V. So this is the kind of equation that we get for the change into the enthalpy. Now, my dear students, we are aware that delta U is nothing but U2 minus U1, and delta V is V2 minus V1. By simplification, we can come to know that delta H is equal to U2 plus PV2 minus U1 plus PV1, or we can write it as delta U plus PV. So again, we have seen that QP is equal to delta U plus PV, delta H is also equal to delta U plus PV, and that is why finally we can say that delta H is equal to QP. So H is equal to U plus PV, H1 is equal to U1 plus PV1, H2 is equal to U2 plus PV2, and that is why finally for delta H even we can write it is H2 minus H1, that is QP, and finally we can say that delta H is equal to QP. It simply means that when heat is absorbed or released at constant pressure, we measure the change in the enthalpy. So my dear students, we in the last period we have proved that heat exchange at constant pressure is nothing but change in the enthalpy. Now to understand the topic better, I would like you to go for uh, this work you should do, that what is the sign of, this is what you need to write uh, in your notebook or homework notebook, that what is the sign of the delta H for the endothermic and exothermic reaction. And this is very important work which you should do in your textbook, that from the textbook you need to find out the method for determining the internal energy change by Bohm calorimeter and change in enthalpy. Now this year, my dear students, this portion from your textbook has been excluded. So I would like to request you to go through this portion and understand how we can calculate the change in internal energy as well as the change into the enthalpy. And I would like you to think about this, that what is the sign of delta H for the dissolution of H2SO4 in water and the dissolution of glucose in water. So these are the two important things that you should do at your home, that what is the sign of change in enthalpy, whether it is positive or negative. If we dissolve H2SO4 in water, or if you dissolve glucose in water. So these are the two questions you are supposed to solve uh, at your home or by your own. And I would like you to think about these changes, what I am talking about. Now, my dear students, we have realized that heat exchange at constant pressure is change in enthalpy, and we are already aware that heat exchange at constant volume is change in internal energy. So let us revise these two important points once again. For isobaric process, for isochoric process, where your V is constant, when heat is exchanged at constant volume, we measure the change in internal energy. And for isobaric process, when heat is exchanged at constant pressure, we measure the change in the form of the enthalpy. So when volume is constant, the heat exchange is known as the change in enthalpy. My dear students, we need to understand about the sign convention. So for endothermic reaction, delta H is positive. Delta H change in enthalpy is positive when at constant pressure heat is absorbed or expansion of the gas. Same way, my dear students, for exothermic reaction, the value of delta H is negative. Delta H change in the that is change in the enthalpy is negative when at constant pressure heat is released by the system, or there is a decrease in the volume of the gas, or there is a contraction in the volume. Third point, at constant volume by the system, if heat is absorbed, that is temperature increases, delta U is positive. If heat is released, now we are studying about the sign convention for delta U, that if the heat is released, if the heat, once again, at constant volume by the system, if heat is absorbed, then we can say delta U is positive. And at constant volume, if heat is released, then we can say that delta U is negative. So this is how, my dear students, we understand the sign convention for delta U. Same way for endothermic reaction, I am giving you once again the revision that for endothermic reaction, delta H is positive, and for exothermic reaction, delta H is negative. This is how, my dear students, we should understand. Now give reason. We need to understand the scientific reason why difference between delta H and delta U is not usually significant for the system containing only solids, only liquid, or solid and liquid. So the reason we need to understand that why the difference between delta H and delta U is not usually significant for those systems where gases are not involved. The difference between delta H and delta U is not usually significant for the system consisting of only solid or liquids or solid and liquid, because solids and liquid do not suffer any significant volume change upon heating. So the difference, however, becomes significant when only the gases are involved during the process. So the difference between delta H and delta U is significant only when the gases are involved into the system or gases are present into the system. Now, my dear students, we want to understand the next question. The next question says that prove that delta H is equal to delta U plus delta N gas RT. Remember here that the new term delta N gas is also a very important term to understand for we people. Let's move forward. Let's consider a reaction that involves gas or gases at constant pressure and constant temperature. We are here thinking about the two variable constant. We are keeping the pressure constant, and we want to keep the temperature even constant. If VA is the volume of the gases for the reactants and VB is the total volume of gases for the products. So VA and VB represents the volume of the gases for reactants and products. If Na is the number of moles of gases present into the reactants, Na is the number of moles of gases present into the reactants, and Nb is the number of moles of gases that are present into the products. Then using the ideal gas law, we can write that this is for reactants. So for reactants, my dear students, we can easily write that PVA is equal to NART, because we are very well aware that PV is equal to nRT. Here the pressure and temperature are made constant, and that is why we are just showing the value of variable for volume and the number of moles of gases. So for VA is the number of moles of VA is the volume of the total volume of the reactants, and Na is the number of moles of gaseous reactants. Same way, PVB for products we can write PVB is equal to NBRT, where VB is the volume, total volume of the gaseous products, and NB is the total number of moles of the reactants. We are well aware that temperature and pressure has been put constant during the change, and that is why by writing the 1 and 2, we can write that PVB minus PVA is equal to NBRT minus NART. Now we are taking the equation 2 minus equation 1. This is the minus sign. So we take the subtraction. So by subtracting the equation 1 from equation 2, we get PVB minus PVA is equal to NBRT minus NART. If we take P common, then PVB minus VA is equal to NB minus NART. This NB minus NA, we call it as a delta N gas. And VB minus VA, we call it delta V, and NB minus NA, we call it delta N. So finally, we get P delta V is equal to delta N gas RT. This is a very important equation to remember. So now we are aware that according to the first law of according to the definition of enthalpy, change in delta H is equal to delta U plus P delta V. Now instead of P delta V, we can write delta N gas RT. Here delta H is change in enthalpy, delta U is change in internal energy, and P delta V is pressure volume work. Thus finally we get delta H is equal to delta U plus delta N gas RT. Here we really wanted to understand, or here we really wanted to prove this equation that P delta H is equal to delta U plus delta N gas RT. That is what we have proved. Now we have the next question. Explain the meaning of delta N gas by the various examples. So here we want to study about the meaning of delta N gas, which we will study by using the various examples. Let us study the meaning of delta N gas. Delta N gas represents the change in the number of moles of gases during the chemical reactions. Remember, here we are talking about only the number of moles of gaseous reactants or gaseous products. So if the reactant or product which are solid or liquid, we are not going to consider them as we are not going to consider them for the calculation of delta N gas. So what is delta N gas? Number of moles of gaseous products, that is the number of moles of gases present into the products. Number of moles of gaseous reactants, that is the total number of gaseous moles present into the reactants, and the difference between these two, or subtracting the number of moles of reactants from the number of moles of product, we get delta N gas. So suppose we have a reaction that is A mole of A gas plus B mole of B gas, that gives C mole of C gas and D mole of D gas, in which A mole of A gas, B mole of B gas react to give C mole of C gas and D mole of D gas. Therefore, number of moles of gaseous product is C plus D, and number of moles of gaseous reactant is A plus B. You can easily see from this equation, my dear students, that this is the number of moles of A, this is the number of moles of B, these two are the reactants, and that is why the number of moles of reactant is A plus B. Same way, number of moles of C is C mole, and the gaseous D product has got the D mole, and that is why the number of moles of gaseous reactant is A plus B, but number of moles of product is C plus D. And that is why we can write that delta N gas is equal to C plus D minus A plus B, where C plus D is the total number of gaseous molecules present in products, total number of moles of gases present in products, and total A plus B represents the total number of gases present into the reactants. So now let us understand this with some examples. Let us look at the first example. Suppose we have equation N2 plus 3H2 that gives twice NH3. So here you can see that the total number of gaseous product is 2 mole, but the total number of gaseous reactants are 3 mole plus 1 mole. Generally, this 1 we do not write in front of the reactant, but it should be if there is nothing written in front of the reactants, or if there is no stoichiometric coefficient written before the reactant or products, that means we should understand it as a 1. So here the total number of reactant gaseous mole is 4, and total number of product gaseous mole is 2. Delta N gas is equal to number of moles of uh, uh, gaseous product NP and number of moles of gaseous reactants NR. And that is why we can write it as delta N gas is equal to NP minus NR. NP here is equal to 2 and NR is equal to 1 plus 3, that is 4. And that is why delta N gas is equal to 2 minus 4, and that is why it is minus 2. Same way, my dear students, when we look at this equation, here we have CaCO3 which is solid, that gives us CaO that is solid, but we get carbon dioxide which is gas. So here we have just gas in the product side, and that is even 1 mole. So here your NP is equal to 1 mole, but your NR is equal to 0. So only one gaseous species involved in this reaction, and that is at the product side, and that is why your NP is equal to 1 and NR is equal to 0. We are well aware that delta N gas is equal to NP minus NR, that is 1 minus 0, and that is equal to delta N gas is equal to 1 for this particular reaction, which is the decomposition of calcium carbonate. Let us understand the calculation of delta N gas for the third kind of reaction. You can see here hydrogen gas, H2 gas plus I2 gas, that gives twice HI gas. My dear students, I have already mentioned that if there is no stoichiometric coefficient present before the reactants or products, we generally consider it as a 1. So here we should consider it as a 1 mole of iodine and 1 mole of hydrogen, that gives us 2 mole of hydrogen iodide gas. Here the total number of gaseous product is 2, and the total number of gaseous reactants, that is your 1 plus 1, that simply gives us 2. So this is how the NP is equal to 2 and NR is equal to 1 plus 1, that is 2, and that is why delta N gas can be NP minus NR, that is 2 minus 2, that is 0. So delta N gas can be 0, it can be a positive value, or it can be a negative value, my dear students. This is how we understand about the delta N gas. Now let us understand one question. If pure water vapor is assumed to be a perfect gas, molar enthalpy change for the vaporization of 1 mole of water at 1 bar and 100 degrees centigrade at 441 kilojoule per mole. Calculate the internal energy change when 1 mole of water is vaporized at 1 bar pressure and 100 degrees centigrade, and when 1 mole of water is converted to ice. So let us think about this problem. Now we are going to solve it. First, the change H2O liquid to the H2O gas, which is known as the vaporization, my dear students. So here vaporization takes place and liquid water turns into the steam. We are well aware that delta U is equal to, delta H is equal to delta U plus delta N gas RT. Now you can see that the product side we have gas, and that is why NP is equal to 1, but reactant side we do not have any gas, and that is why we write NR is equal to 0, and therefore delta N gas is equal to 1 minus 0, that is 1. The value for delta H is given as 41 kilojoule per mole, that is 41,000 joule per mole. This kilo multiplied by 1000, and here the value of R is 8.314 joule per mole per Kelvin. As the value of R is in joule, we need to convert this value of enthalpy, which was in kilojoule, to the joule. So we are well aware that delta H is equal to delta U plus delta N gas RT. We know that temperature is 100 degrees centigrade because vaporization takes place at 100 degrees centigrade, that is 373 Kelvin. So we can put all the values into the equation delta H is equal to delta U plus delta N gas RT. For this equation, we converted delta U is equal to delta H minus delta N gas RT. The value for delta H is 41,000. For delta N gas, we write 1. This 1 is for delta N gas. This is 8.314 is the value for R. And this is the temperature at which this change takes place. That is at boiling point of water. And by doing the calculation, we finally get the answer. Change in internal energy is equal to 37.904 kilojoule per mole. Now, my dear students, we want to understand the second case. So, we'll study about the case number 2. In case number 2, 1 mole of water is converted to ice. That means H2O liquid turns into H2O solid. Now here there is no gaseous reactants or products are available. One is water liquid, another is solid ice, and that is why delta in gas is equal to 0. Now we have already discussed, my dear students, that if only the solid or liquids are involved during the chemical change, there is no fair difference between the change in internal energy as well as the change into the enthalpy, and that is why here your delta N gas goes to be 0. So no gaseous molecules are involved, and that is why delta H is equal to delta U plus delta N gas RT. We know that value of delta N gas is 0, and that is why delta H is equal to delta U. And that is why delta U is even equal to 41 kilojoule per mole. So with this example, my dear students, we truly understand about the difference between delta H and delta U, and we can even understand that the difference between the change in enthalpy and change in internal energy is only significant, is only meaningful when the gaseous reactant or products are present during the chemical change. Now, my dear students, we want to study about the two important terms. One is known as the extensive property and another is known as the intensive property. Let us study about or let us define these terms, extensive property and intensive property, and we will explain them with the examples. So first, let's study about the extensive property. An extensive property is a property whose value depends on the quantity or size of the matter present in the system. So for example, if we consider these extensive properties, that we have temperature, density, mass, volume, internal energy, enthalpy, and heat capacity. So on the basis of this, we can truly understand about the extensive property. The important point that we need to remember is that extensive property depends upon the quantity and size of the matter present in the system. So if the thermodynamic property depends upon the quantity of size and size and quantity of matter present in the system, we call it extensive property. Now we will study about the intensive property. Those properties which do not depend on the quantity or size of the matter present in the system are known as the intensive properties. Let us look at the various examples of the intensive properties. They are temperature, density, or pressure. So my dear students, if you have 1 kilogram of water and you have 5 kilogram of water, if you measure the temperature, and if so, it is possible that both the water have same temperature. The density of water is 1, it is universal, and it is for any quantity of matter, the density of water remains 1, and the pressure exerted on gas, whether it is 1 kilogram of gas or it is 10,000 kilogram of gas, the pressure remains same. So that is why we can call this properties as a intensive property. They have intensity, they do not depend upon the matter or size of the system. Now let us understand the same with one example. So suppose we have a container in which the volume is V and temperature is T. Now we divide this container uh, with the partition so that the volume become half, V by 2, V by 2. But the temperature again in both the cases remains constant, and that is why we can say that volume is an extensive property whereas temperature is an intensive property. Let us read the text and understand it well. Let us consider a gas enclosed in the container with the volume V and the temperature T. Let us divide the container in two halves by making a partition such that the volume is half. So volume has been halved. Each part now has one half of the original volume, that is V by 2, and but the temperature still remains T in both the half, and the temperature remains same in both the half. And that is why we can say that the volume depends on the size and matter, but the temperature does not depend on the size and matter. So volume is an extensive property, whereas temperature is an intensive property, my dear students. This is what we can easily understand. So I hope, my dear students, today you have enjoyed your class. If you have doubt, you can ask. And I wish you happy learning. Hope you have enjoyed the class. Happy learning.